Before an MCP server exposes tools, data, or prompts, it needs to know who or what is calling. In production, that identity may be a user, an AI session, a client app, or a backend service. Authentication makes everything else safer. You've already built a practical model of MCP servers, from production architecture and lifecycle to minimal implementations that can grow safely. You've also identified threats like tool misuse, confused deputies, excessive permissions, data exposure, and untrusted clients. The next question is foundational. Who is actually making the request? Authentication establishes identity before authorization, policy, delegation, and auditing can work. For production, MCP, authentication is not just asking, is there a user? A single request may carry several identities at once. The client application, the human who initiated the task, the AI session acting on their behalf, and any backend services involved in fulfillment. Before processing a tool call, resource read, or prompt access, the server needs a trustworthy, authenticated context. That context may come from OAuth or OIDC tokens, an API gateway, mTLS, signed service credentials, or platform identity. Only after identity is proven should authorization decide what actions are allowed. In MCP, who made this request is really a set of related questions. The client application proves which AI product or integration connected. The human identity tells you whose authority and data are involved. The AI session identifies the specific conversation, agent run, or workflow that produced the action. The backend service identity shows which internal component actually executed it. Keep these identities separate in tokens, logs, and policy checks. If they collapse into a single user, you lose the ability to tell whether an action was allowed, delegated, automated, or performed by the wrong service. Think of an MCP server like a security desk at an office entrance. It checks two things. First, is the access channel approved, like a registered app or managed device? Second, who is the person behind the request, and are they allowed to do this? A trusted application can still carry a risky user action, and a legitimate user can still arrive through an unsafe or unapproved client. Strong MCP security treats these as separate gates, because each answers a different question. AI interactions often span more than one request. One user prompt can trigger an agent run, several tool calls, and a chain of intermediate decisions. Session identity ties those events together. It also separates two conversations from the same user in the same client app, so activity does not blur together. In practice, pass stable context, such as a session ID, run ID, trace ID, or conversation ID with each call. That gives teams a reliable thread for monitoring, abuse investigation, rate limiting, and audit correlation. When an MCP server calls a database, queue, API, or third-party service, it crosses a new trust boundary. That downstream call needs its own service identity, not a reused user token. The service can prove itself with mTLS, workload identity, signed JWTs, IAM roles, or short-lived credentials. At the same time, do not drop the original caller context. Downstream systems often need both facts: which backend component made the request, and which user or session triggered it. That preserves provenance, supports authorization, and makes auditing meaningful. A production MCP server should not let every tool or policy module interpret tokens differently. Instead, it should verify the incoming evidence first, such as OAuth tokens, SAML assertions, or trusted gateway headers. Then it should convert that evidence into one internal authentication context: client, user, session, tenant, scopes, method, claims, and assurance level. That context becomes the shared input for authorization and audit. The key rule is source integrity. Raw identity fields are only claims until they are cryptographically verified or delivered by a gateway you explicitly trust. OAuth and OIDC are often mentioned together, but they answer different questions. OAuth 2.0 asks, what is this client allowed to access? It issues access tokens and sometimes refresh tokens, so an MCP server can authorize calls to tools, resources, or downstream APIs. OpenID Connect builds on OAuth and asks, who is the user? It adds ID tokens and identity claims for the client application. The important rule is not to swap token purposes. An ID token proves identity to a client. It is not automatically an API permission slip. Here's the core flow. The MCP client never needs the user's password. The user signs in with the identity provider. After successful authentication, the client receives a short-lived authorization code. The client then exchanges that code for tokens over a secure back channel, not through the browser. For public clients, PKCE binds the exchange to the original request, reducing code interception risk. After that, the client calls the MCP server with an access token, and the server validates it before allowing any tool or resource request. Treat tokens as different credentials, not interchangeable passwords. An access token is what an API or MCP server should see. It proves the request has specific permissions, and it should be short-lived. An ID token is for the client application. It tells the app who the user is, but it is not the authorization ticket for backend calls. A refresh token is the long-lived key that gets new access tokens. That makes it powerful, so store it securely, rotate it, and revoke it quickly when risk appears. Accepting a bearer token is only the starting point. The MCP server must prove the token can be trusted before using anything inside it. First, verify the signature against the issuer's current keys, usually from JWKS metadata, or use introspection when the provider requires it. Then validate the core claims: issuer, audience, expiration, not before, subject, tenant, and client identity when relevant. Audience and issuer checks are especially non-negotiable. Only after those checks pass should the server evaluate scopes and claims to decide what the request is allowed to do. Most MCP servers should not become identity systems. They should delegate sign-in and token issuance to a trusted provider like Okta, Entra ID, Auth0, Cognito, Keycloak, or Cloud IAM. The server then validates incoming tokens using provider metadata, preferably OIDC discovery and JWKS, so signing keys are not hard-coded. After validation, provider-specific claims are translated into a consistent internal auth context: user, tenant, roles, scopes, and policy inputs. The operational work is planning for key rotation, issuer changes, separate environments, and multi-tenant configurations before they become production incidents. Service accounts are the right model when software, not a person, needs access. Scheduled jobs, backend workers, CI pipelines, internal services, or trusted integrations. Treat these identities like powerful production credentials. Give each workload its own identity, then scope it to only the tools, tenants, resources, and environments it truly needs. Prefer short-lived tokens that rotate automatically, so leaked credentials expire quickly. The dangerous pattern is one shared admin secret with broad access and no rotation. That turns every connected system into a potential path to compromise. Authentication is the foundation for every secure MCP decision. In production, you are identifying more than a user. The client app, AI session, and service identities matter too. Use OAuth and OIDC patterns, validate every token rigorously, and keep machine credentials short-lived, scoped, and auditable. With identity established, you can enforce policy, consent, tenant boundaries, and accountability.